Energy and heat are probably terms that you've heard of before, and you probably have a pretty good idea about them. We're going to take a look at energy and heat, and we're going to continue to dive a little bit further into these concepts because really energy is such an essential component to really all of the sciences. And since chemistry is where a lot of this is taking place, we really want to dive into where the chemical energetics actually occur. So grab your Cornell notes and let's get started. So when we think of energy here in the Pacific Northwest, we oftentimes think about the energy that we get into our houses, or our electrical energy. And where does that energy come from? Well, we have a certain proportion of it that actually comes from dams. So here's Grand Coulee Dam. We have some dams here in the Spokane area, down at Riverfront Park and um, out at Long Lake, that we are able to get energy from those hydroelectric dams that are providing us with energy. And so basically, the kinetic movement, we have some potential energy of the water that's behind the dam. And when we have the kinetic movement of the water through the turbines, it actually is going to transfer and transform that energy into an electrical source that we can use. In more recent years, we've seen a variety of wind turbines that have started to kind of dot the landscape for us. And so this is a newer form of energy harvesting that we see. We can actually even see it in electrical storms, or even as we're using our different power stations and electrical pathways to move them from one place to the other. And you think about it, what does this energy do for us? Well, it's able to power our computers and maybe our mobile devices and our televisions and how we're going to cook our food and a whole bunch of things. If you think a little bit more about it, we actually have energy even within our living systems. And so whether it's for our car or whether it's for our bodies, we will take in molecules. So gasoline could be a molecule. This isn't necessarily gasoline. Or we can take in macromolecules and break them down into things like glucose and fructose. And we can end up breaking apart these bonds that hold these arrangements of atoms together in this molecule. And when we do that, we can release some of that or harvest some of that energy. So it's kind of like how dams work as well, as we're actually just harvesting that energy that we're able to attain through just kind of the kinetic, or excuse me, the potential energy that's held within that, and move that into kinetic energy so that we can do work. If we're thinking about doing work in a car, we're thinking about running an engine. If we're thinking about doing work in our bodies, we're thinking about making ATP that can drive all of our other chemical reactions and our ability to move. And so kind of keep that in mind. No matter what we're doing, this energy is super vital and important for everything that really happens within us and around us. And so what is energy? It's the capacity to do work or to produce heat. And a lot of times we end up doing both, because most of the time, even when we do work, we give off some heat. A lot of times we want to be able to do that work, unless maybe we're building a campfire and we just want to get some heat from that. We have some forms of these energies, and we're really going to focus on how does this relate to chemistry. And so you've probably heard of kinetic energy before, but as far as chemistry goes, how are we able to use that energy of motion of our particles or our molecules in order to look at energy? And so we've done a little bit of that before. And then the potential chemical energy, or the energy of composition. And so we're going to be looking at these as we work through many different kind of simulations and applications of chemical energy. And so with that, we have the types and the number of bonds, or the atoms that are involved, and the arrangements of them as well. And so both are important. And so really this is the study of thermochemistry, or energy changes in chemical reactions and changes in state. And it's for both of them. So when we have phase changes, we also see that energy is going to apply. And that's really going to be between making and breaking intermolecular forces, where with chemical reactions, it's really about making or breaking those chemical bonds that hold them together, as far as either covalent or ionic bonds. And so they all are going to be related back to this energy. And so when we do different processes, it's really just a different process of of what's happening, whether it's changing state or whether it's changing the chemical, but the bigger idea or concepts behind them are going to be quite similar. So the question is, how is energy changed? Well, energy changes occur as heat is transferred and or work is done. And so a lot of times both happen. So if you are running your internal combustion engine in your car, the work is being done because you're able to drive your car, but you're also producing some heat, which is why you need oil to reduce friction and you don't want to seize your engine up. Energy is absorbed or released as chemical bonds and or intermolecular forces are formed or broken. And so that's what I said. It relates both to those chemical and physical processes. So we end up having heat that is transferred, and it's between objects or between substances. So how does that heat flow? Well, we have the entire universe. So if you think of all of the black space behind here as being the entire universe, and the area that's going to be closest to whatever we're looking at is going to be called the surroundings. And whatever system we're actually looking at is going to be our system. So we have system and the surroundings, and all of it encompassed is actually going to be the universe. Okay? And so what we see is we have system where things could be occurring here. So say we had, let's grab the blue one, say we had some energy that was being transferred from the system to the surroundings. Okay, so we're going to have energy flow this way because there's a difference in energy. And so what we would see is that there would be a greater amount of heat here, okay, and a lower amount of heat here. And so it's going to transfer from where there's more heat to where there's less heat. Okay, and if we're moving in that direction, we're actually going to call that a certain type of reaction that is going to be exothermic. Okay, this is exothermic, where the system is giving off energy. And so when we talk about endothermic and exothermic, we're talking about the system itself. If the system is doing the opposite, say it is absorbing energy, so my E is my energy, and so say we're absorbing energy, and so we have a greater amount of heat outside compared to inside, okay, over here, this would be endothermic. Okay, and so we're absorbing. Now, I know we've already talked a little bit about activation energy. Yes, there's a little bit of, no matter which one of these that we're looking at, there's a little bit of energy that has to be initially absorbed. But overall, is the reaction going to absorb energy or is it going to give off energy? And so we have this energy of the universe is always conserved. So no matter what, the energy is just being transferred between the system and the surroundings, but the total amount of energy actually remains the same. Heat flows from warmer objects to cooler objects, and so that's what we were saying, from the greater amount of heat to the lower amount of heat, or from cold or from warm to cold. Energy of systems. Okay, the endothermic system absorbs energy from the surroundings, and the exothermic system gives off energy to the surroundings. And so we're talking about what's that energy transfer of the system itself. So just a little bit more on how heat flows. If we want to determine the amount of heat, or we're going to throw another term in there, heat can also be called enthalpy, that's transferred, we often evaluate the system using temperature, and we need to also know the amount of substance. And so what we see is this delta H means the change in heat, or the change in enthalpy for our entire process in our system, is going to be equal to the heat of the final state of the system minus the heat of the initial state of the system. And so we're looking at that overall change. If it's an endothermic process, the delta H is going to be positive, and if it's exothermic, the delta H is going to be negative because it's lost some heat. And this is something that people oftentimes get mixed up. So make sure that you write this down somewhere and keep that safe and look back at it, because that is a question that's going to come up later on. So how is energy measured? Well, we've talked about these units before, and we have calories. And you've probably heard of calories before because you eat some food, and in that food we say that there's some calories, but the food calories that you eat are actually kilocalories. And the calories that we're going to use for our purposes in chemistry class is going to be, 1,000 of those calories would be 1 kilocalorie. And it's the amount of energy required to raise 1 gram of water 1 degree Celsius. You'll see later where that applies with calorimetry. And we also have the joule, and the joule is the SI unit of energy, so a lot of times we use that for many of our calculations. And if you want to convert between joules and calories, 1 calorie is equal to 4.184 joules. And so that's a good conversion to have somewhere so you can get from one to the other if need be. So specific heat is going to be something that we want to also know about. So we have this thing called heat capacity. It's the energy to raise an object 1 degree Celsius, and it depends also on the mass and the chemical composition. And so we really want to know about the specific heat capacity. So specific heat actually is the specific heat capacity, which is the energy required to raise 1 gram of a substance 1 degree Celsius. We can use this to identify different substances because all substances are going to have a fairly unique heat capacity. And so we can have this relationship between heat of a system and heat capacity and temperature, and this is our equation. So the Q of the system, this represents heat, so we can represent heat using a Q or using an H, and either way is fine with me. So if you want to replace that with an H, that's okay with me. So Q is actually going to be H, or heat, okay? Heat. And C is going to be the specific heat, M is the mass, and delta T is the change in temperature. And so we can see this down below where Q is heat, C is specific heat, M is mass, and delta T is the change in temperature. And so it's the final temperature minus the initial temperature. One other thing to keep in mind is that as we are looking at the system, if the system is has a positive value for its heat, then the surroundings would have a negative, because remember, what one gains, the other one will lose, and vice versa. And so that's something to keep in mind. And sometimes we'll actually evaluate the surroundings rather than the system to learn about the surroundings. So those are going to be important things to kind of keep in mind as we do some practice later on. So let's do a couple of practice problems on how to calculate specific heat first, and then we'll calculate just the heat of a system. And so the first one here is going to be, what is the specific heat of copper if a 20-gram sample of iron increases from 25 degrees Celsius to 68 degrees Celsius and absorbs 395.6 joules of heat? So again, we're going to use this equation. Q is equal to C M delta T. And in this case, we want to know the specific heat. Well, the specific heat is going to be our C. So we're going to plug in everything else. G is going to be our mass. The 395.6 joules is going to be our Q. That's our heat. And then our change in temperature is the change between these. So we're going to plug these in. So 395.6 joules is equal to some value of C times 20 grams, and then times the change in temperature, which is the final temperature minus the initial temperature. So I take my 68 degrees Celsius and I subtract from that 25 degrees Celsius. Okay. So in order to solve this, let's see, 68 minus 25, that should give us a total of 43 degrees Celsius. So I can just automatically do that. So to find C, I'm going to have to take C is equal to 395.6 joules divided by 20 grams times 43 degrees Celsius. And when I calculate that out, I should get 0.46. And our units for specific heat are always going to be joules per gram degrees Celsius, and it's a derived unit there. So that would be how to calculate for specific heat of a substance if you didn't know what it was. And sometimes we need to find out so that we can determine what type of substance that you would have if you had an unknown metal. Okay. All right, let's take a look at one more example problem before we're done here today. And that's going to be to determine the heat. So again, if we have Q equals C M delta T, Now we want to solve for Q. How much heat? So that's going to be Q is absorbed if 500 grams, that's our mass. Here's our change in temperature. So delta T is going to be, this one is our final, this one's our initial, so we'll take the difference between those two. And then this here is our C, it's our specific heat. So Q is going to be equal to 0.90 joules per gram degree Celsius for our specific heat times the mass of our 500 gram aluminum pan that we're going to heat up from 25 degrees Celsius to 198. Now you have to do 198 minus the 25, okay, to get your degrees Celsius. And so when I calculate that whole thing out, we're going to have degrees Celsius cancel, grams cancel, we're left with joules, which is our energy unit, and that's what we want to know. And we end up with 77,850 joules. Now, with sig figs, let's see, we should have 2 sig figs. So that would be with sig figs 78,000, excuse me, 78,000 joules. Okay, so those are just a couple different ways that we can calculate these, and we will do some practice when we get back to class.